Between Newton's work and Einstein's, we can account for observations regarding gravity to extraordinary precision. What is left to explain is the mechanism. Neither Newton nor Einstein tells us why mass attracts mass. Newton was explicit about this. He described gravity with perfect mathematical precision and refused to speculate about its cause. Einstein replaced the force with curved spacetime, but didn't explain why objects had to follow that curve, only that they do. What is it that is curving? How does mass cause the curving? In wave physics, when a knot forms in the membrane, it extrudes material out of the two-dimensional plane into the third dimension. That material has to come from somewhere. The membrane is a physical surface with conserved area, so forcing material up into a knot leaves a deficit in the plane it just came from, a zone where the membrane is less densely packed, less tense, and more flexible than the surrounding membrane. For a small mass, that difference is negligible, but when trillions of atoms are combined into a celestial body, the cumulative effect is a zone of reduced tension around that body. The more massive the body, the larger the zone. That is its gravitational field. The membrane farther out, in deep space, is fully populated and under maximum tension. It pushes inward from all sides. An object sitting in the tension gradient of a gravitational field is pushed harder from the deep space side than from the side near the mass, because the membrane near the mass is at increasingly lower tension the closer one gets to the surface of it. Weight is based on the number of connections an object has with the membrane, which is generally the number of knots it's composed of. The more knots, the greater the total push from the membrane towards the planet, the greater the weight. However, a bowling ball and a feather are going to fall at the same rate, because the acceleration of gravity is based on the time an object is exposed to the changing tension gradient of the membrane around a celestial object and the height at which they start falling. If you let a bowling ball and a feather drop from the same height at the same time, they will both be reconstructed at the same rate as they fall, because the acceleration of the objects is due to the change in the tension gradient in the membrane around the planet, and the refresh rate of the membrane, which is the same for both objects. This dynamic might hold the key to anti-gravity. Just as a magnet creates the conditions for the membrane to move objects without consuming the magnet's own energy, anti-gravity can potentially be achieved by creating the conditions for the membrane to cause matter to be directed away from a mass instead of toward it. How exactly to do this? We don't know yet, but the theoretical foundation exists for anti-gravity to be mastered, and for interplanetary travel to be accomplished without the cost or the danger of rockets. This could also have a tremendous effect on the cost of travel on Earth, by removing the friction caused by gravity. Another factor about gravity is that it has a finite range. The tension deficit created by a mass spreads outward through the membrane, but it dilutes with distance. At some point, the gradient becomes too small to resolve against the background tension of the membrane, and beyond that point, the gravitational influence simply ends. It does not taper off to infinity. It stops. For the Sun, that terminal range is approximately 70 light-years. Every star within that radius, including our nearest neighbors, lies within the Sun's gravitational footprint, and the Sun lies within theirs. The solar neighborhood is not a collection of independent systems sharing a region of space. It is a mechanically coupled network. One more point, because it has become one of the most celebrated results in modern physics. LIGO, the gravitational wave detector, has detected signals from events like neutron star mergers over 100 million light-years away. These have been interpreted as gravitational waves, ripples in space-time propagating from those distant collisions. Wave physics does not dispute the detections. It disputes the interpretation. The gravitational footprint of a neutron star extends, at most, a little over 100 light-years. A merger 130 million light-years away cannot send a gravitational tension differential to Earth. Its field never reached here in the first place. What LIGO detected was an impact wave, a transient mechanical disturbance in the membrane produced by the catastrophic collision of two massive objects, with the impact wave propagating outward at the speed of light. LIGO does detect gravity. It continuously measures the tidal deformations produced by the Moon and the Sun. What it detected from those distant mergers was something else: the membrane's report of a collision, not the gravitational field of the objects that collided. In the next video, we will discuss relativity.